So, yeah, good morning, students. So, if you see, if you recall last class, this is the moment where we stopped with. So, for any control volume that we have seen, if this is a control volume at steady state, for this to happen, normally if you write the conservation equation or like entropy balance equation, basically this is the entropy balance equation that is with us, and we have written this equation. So, if you see entropy that is getting in terms of either mass or heat interactions were taken into consideration, and heat entropy doesn't get transferred by virtue of work. So this, if you make some assumptions, like if you close the system, basically if mass inflow and outflow are not allowed, then we have seen how this control volume approach can be detected to a closed system approach. And for irreversible process, this S generation is 0. That's what we have stated here. So for irreversible process, S generation is positive. We have seen doing a analysis for entropy. So with these three equations, these are the three basic equations for any system and any surroundings that could give something for you to calculate entropy change of universe or entropy of change of the system or surroundings and all these things. So these are the only two equations which you need to take care of. This is for closed systems to calculate entropy change of a control volume, and this is for the closed system. So now, depending upon different process or depending upon whether the process is reversible or not, we'll consider this term or we'll neglect this term. So all these things matter. So with the knowledge of these two equations, we can solve all the previous gate questions of entropy. Okay. So now we'll learn how to solve. We'll look at previous gate problems. Okay. Just a second, guys. So we'll see all the questions. Okay. Okay, so yeah, this is the first question we could work out. So see here, the 1 kilomole of an ideal gas is throttled from an initial condition of, let us use this color. So 1 kg of an ideal gas is throttled from an initial pressure of 0.5 megapascals to 0.1 megapascals. And it's a common experience for us, as if you throttle a gas, this throttling will definitely cause some pressure drop. The initial temperature is 300 Kelvin, the entropy change of the universe. So let us see. Let us suppose there is a throttling valve and we are throttling some fluid. Okay, of course it's a small throttling device. Now if you take this throttling device as the system, something here, now everything external to this is surroundings, correct? And this throttling valve that we have taken is the system. Okay, so if this is system and this complete thing is surroundings and this combination is universe, now they're asking for the entropy change of the universe. So if you want to calculate entropy change of universe, you need to know entropy change of the system and entropy change of the surroundings. Now if you see, when the throttling is happening, is there any heat transfer to the surroundings? Please tell me, is there any heat transfer to the surroundings when throttling is happening? For small devices, for small throttling devices, for small throttling devices, what's happening? This Q of heat interaction is 0, okay? Which means out of this throttling device, no significant amount of heat interaction is taking place. And as per steady state energy equation, we also have delta H is equal to 0, which means delta T is equal to 0, because one term is mentioned here. It's mentioned the system is ideal gas. So if the system is ideal gas, for ideal gas we have H is equal to Cp into T. So this implies dH is equal to Cp into dt. So if this is 0, yeah, because time is very less. Correct, that's what we discussed during throttling of steady flow energy equation. So if dH is 0, this means dt is also 0, which means one thing that we can assure at this moment is T initial is same as T final, and there is no heat interactions. This is what we must know. Now please tell me, when the system is very small, we can treat it as a closed system, then this surroundings, there is no heat transfer into the surroundings. So which means if you want the total entropy change of the universe, we can write it as delta S of the system plus delta S of the surroundings. And since during throttling only heat is the only possible source that can go out, but in throttling process we don't have any such heat interaction that is going out of the system, this delta S surroundings is 0, because the throttling devices are very small devices. Generally we don't have considerable amount of mass inside the throttling device, so when compared to the surroundings, so it can be treated as a throttling can be treated as an isolated system where mass and energy are not going out. So now if you see this case, this delta S of system, now during this in this system, in this device, what's happening? Temperature is constant. I mean T1 means T initial is same as T final, but there is pressure drop. Initial pressure value is given as 0.5 megapascals and final pressure value is given as 0. What's the data that's given? 0.1 megapascals, correct? Yeah, 0.1 megapascals. And did they mention something? 1 kilomole of ideal gas. Okay, mass is 1 kilomole and initial temperature is 300 Kelvin. So this T final is equal to T initial is equal to 300 Kelvin. Now why I am equating this initial temperature to final temperature? Because throttling is ideal, working substance which is undergoing throttling is ideal gas. So if you want to calculate this delta S of the system, since this ideal gas is undergoing the process, we know temperatures and we know pressures, so we can write minus R ln P2 by P1 plus Cp into ln T2 by T1. This is for the delta S of the system. Correct? Since mass flow rates are not given, we know we don't treat any significant amount of mass is traveling into the surroundings, and also we know for throttling temperature, heat interaction with the surroundings is also 0. We assume that this delta S of surroundings is 0, because if mass and heat are not going out of the system, we treat that system as an isolated system. Correct? So there is no heat interaction with the surroundings, and you can see this change in entropy of the surroundings is 0. Now, if T initial is same as T final, then what could be this value? 1. And what could be this total log value? 0. Correct? So this is equal to, so delta S of universe is same as delta S of the system now, minus R. In place of R, can we write, see, you have R is equal to, see, RU by molecular weight, of course. It's given 1 kilomole, it's given in moles. So if you apply PV is equal to N RU into T, if you apply this, so pressures and initial temperature, you can find what is capital volume, because N is known, RU is known to you, temperature and pressure at initial conditions are known to you. So you can write volume. So if you take R value, R is nothing but PV by T. Of course, if you are dealing for kilojoule per kgs at the end. So if you see here, this R can be written as PV by T into ln P2 by P1. This is the value, and for value, let us write, suppose we are writing at the initial conditions, so minus P1 by T1 into, what's the formula that we can write for initial volume? From this, N times RU into T divided by P. So N times RU into T divided by P. If you write this, we have ln P2 by P1. So now you can calculate the values, because things get cancelled off here. Please tell me what are the values. P1 is known to you, P final is known to you, T1, of course, T1 and P gets cancelled. Number of moles of gas is also known to you. So please tell me what could be the value here. See, you have all the data here. N, RU is 8.314 kilojoule per kilomole. So now you can calculate the values. Please calculate and tell me what could be the value. Use calculator and tell me the values. Of course, this is 1. We are writing at state 1. So during throttling, pressure drops and entropy is, of course, increases. So this total outcome value should be something positive. Okay. So please tell me what could be the answer for this. Okay, let me perform the calculations. I think it's taking a bit time. So I can cancel this T's and this P's, and N times of Ru into ln P2 by P1, and N is 1 kilomole and this Ru is 8.314, and log values we have. So if you calculate the values, we'll be getting something around 8.314 into 5 ln. So if you calculate this, 13.3 is something that you're getting, correct? Yes, Vamsi, correct? 3 something. Okay, 13.38. So if you would like to enlarge this a bit, this value is 13.38 kilojoule per Kelvin. So this is the total entropy change for this process. So which means you have seen this delta S of the system is equal to 13.38, and throttling is an irreversible process. This delta S of the system can be written as integral del Q by T plus S generation. But since there is no heat interactions, that integral del Q by term is 0. But whatever you're having here as the delta S of the system, that is due to entropy generated due to throttling. And entropy generation is always positive, which you also got here as 13.38. So if you can see this 13.38, which is here, could be the reasonable correct answer. Okay. Did you all understand this question? Why it's 13.3? Because of this calculation that you have. Anyhow, n value is 1. So if you perform this calculation, this P2 by P1 is actually 1 by 5. So if you write that as log 5, this minus sign gets eliminated. So that's how I multiplied 1 into 8.314 into log 5 value. Clear? Nothing big involved here, but just simple application of entropy balance equation. Okay. Next, we'll go for the second question. So please see this question. A system undergoes a state change from 1 to 2. According to second law of thermodynamics, for the process to be feasible, the entropy change S2 minus of the system is. Please tell me what would be the correct option out of these 4 questions. See, it's given the system is executing the process, correct, from state 1 to state 2. Means, for example, if you take some process, random process 1 to 2, let us suppose there is a process, something like this, on 2 coordinates. Some process, doesn't matter what are the coordinates you take here. So for the process to be feasible, the entropy change S2 minus S1 of the system is. Please tell me what could be the answer for this. Okay, I'll give you time to think. So please think and tell me what could be the answer. See, it's a simple question. See, let us suppose your system is undergoing a reversible process. Option A, positive or 0. Actually, along with positive or 0, it can be negative as well. See, I will show you. Reversible process. Let us suppose system is undergoing a reversible process. Now, if system is undergoing a reversible process, we have ds is equal to del Q by T. And this denominator is always positive. Now, this can take any 3 values, correct? It can be less than 0 if heat is rejected. This can be equal to 0 if process is adiabatic. And this can be greater than 0 if heat is added. If heat is added. Correct? In an adiabatic system, when this del Q is 0, this numerator is 0, so this ds is 0. And of course, we know reversible adiabatics are known as isentropic process. In yesterday's class, we have seen that. Now, if some heat is getting out of the system, then this del Q is negative, but this temperature T in absolute scale is always positive. So this del Q by T term will always give you something negative if heat is getting rejected out of the system. But if heat is added into the system, then what happens? This del Q is positive, so we can get a positive sign. If process is irreversible, this is irreversible. So if process is irreversible, see what happens. We know delta S is equal to integral del Q by T plus S generation. Correct? And this term is always positive, of course. But what about this term? This can be positive or 0 in case of adiabatic, or it can be negative. So depending upon numerical values which the process is executing, this value ds, this total delta S can be less than 0 if this quantity, means if heat ejection is very much more when compared to the entropy generation, or this can be equal to 0, such that whatever this value numerically is giving is same as the entropy generated, or this can be greater than 0 if in a process both entropy, of course entropy generation is anyhow positive, but if also heat is added, then this value can also be positive. So in these three processes also, in these three cases, delta S can be greater than or equal to 0, or it can also be less than 0. So anything can happen, but entropy generation is always positive. But in a process, entropy change can be negative, means entropy can decrease, because if some heat is getting out of the system, as you have seen here, if delta Q, if heat is getting out of the system, your entropy will decrease. Correct? So for a process, if it's executed from state 1 to state 2, any of these things, these three things can happen. So answer can be either positive or 0 or negative, doesn't matter. Okay, clear, understandable to all of you? Why it can be negative as well? It is positive or 0, because for reversible adiabatic process, entropy remains constant, and for this process of heat addition, this is positive, but it can be less than 0 if heat is being ejected by the system. Means if this del Q is negative, then this can be come out as a negative quantity. Clear, understood to all of you? Why a system can have positive change of entropy, no change in entropy, or a negative change of entropy? Understandable to all of you? See, just basic definitions. I told you on the starting day that ds for reversible process is del Q by T. I have applied that, that's it. No issues, nothing. Total entropy chapter runs only on one equation, entropy balance equation, that's it. Okay, so see here. See this question. 1 kilogram of water at room temperature is brought into contact with a high temperature thermal reservoir. So if you see here, there is some 1 kg of water. So there is 1 kg of water. Okay, fine. Let us change color now. This is 1 kg water. Now this is brought into contact with some thermal reservoir. Which is at a higher temperature. Of course, this is at some higher temperature. Then obviously what happens? Some heat gets flown into this. Correct? Some heat gets added into this system, because reservoirs are the sources where they'll supply some work without any significant change in their temperature. So if you bring this water close to this reservoir, then what happens? Some part of heat from this reservoir will get transferred to this water. Okay. The entropy change of the universe. So if you see, if you consider this water as the system, so let me use this color. If you take this water as a system, then some heat is being added into this process. Correct? So delta S of universe is equal to delta S of system plus delta S of surroundings. Now you see one thing very carefully. Normally if you see, if this is system and the reservoir is surroundings, and if both together form the thermodynamic universe for assumption. So now see carefully what happens. This delta S of system, heat is added to the system, correct? Of course. And this delta S of surroundings, this time there is small change in delta S of surroundings as well, because some heat transfer is occurring from surroundings to the system. So let us suppose this is integral del Q by T, where this temperature is initially from the initial temperature of water to final temperature, which is TH, because heat transfer stops once these two attain thermal equilibrium, minus, because from surroundings there is heat loss, minus QH divided by TH. This TH is constant throughout the process, and TH is greater than Ti. Correct? That's why we are running the integration from Ti to Th. Now please tell me, if you compare numerical values of these two, at the end total heat that transferred into the water is same, because whatever the heat the reservoir is losing, the same heat this water is gaining. Now tell me, when this T is changing from Ti to Th, by the time that total heat Q is transferred into the water and this Th is constant, tell me numerically, if you compare this integration with this QH by TH term, tell me which value will be more, integral or this algebraic? T is less than TH, correct? Initially for some part of the process, I mean till the end of the process. Now tell me, out of these two values, which value will be numerically more when total heat transfer is same in both the cases? first, correct? This integral will be more because you see denominator is small when compared to this. See, for total duration of heat transfer, here the temperature is TH. But here, if you see, only for the final last part of the heat transfer, the temperature is TH. But for all remaining parts of heat transfer, means if you basically divide this heat transfer into number of processes, then in every process, this temperature Ti or the intermediate temperature somewhere in between is less than TH. So this integral value will be definitely more than this value. If this is the case, what would be total change? This is greater than 0. Okay, if you can apply minus mc ln T2 by T1, and if you compare the values, you can get positive value. And of course, it should be positive because heat is transferred between finite temperature difference. The temperature of this water is not same as this TH. So if you see, heat transfer is occurring at some finite temperature difference, and heat transfer to finite temperature difference is always irreversible. When the process is irreversible, we always have S generation. So which means this process will always have positive change of entropy. Did you all understand why this integration term will be more than this QH term? It's a simple logic. And also you can see heat transfer to a finite temperature difference. See, delta S of the system, either you consider for a reversible or irreversible process, delta S value is same, correct? But yeah, of course, if you want, you can add plus S generation here. Anyhow, that's also positive because this S generation term is also positive. Okay, so this is always positive. So plus S generation, this term is also positive. So if you see, this whole result will be positive, which means the entropy change is always positive when some heat is added to the water. Okay. Clear? Did you all understand why this term will be more than this QH by TH? Because this TH is constant throughout the heat transfer. But here if you see, this T is somewhat low than this TH for most of the part of this process. So which means this value will be numerically more because this T is less when compared to this TH. Okay. So we are going for next question. So see this question, it's given something. Consider the following two processes. A heat source at 1200 Kelvin loses 2500 kilojoules of heat to a sink at 800 Kelvin. A heat source at 800 Kelvin loses 2000 kilojoules of heat to a sink at 500 Kelvin. Which of the following statements is true? So see here. See, please respond. Okay, I want your responses. Otherwise, it's really difficult to teach thermodynamics because I don't know whether you're understanding things or not. It's a basic science, and we need interaction with the students. Okay, so see. Solution. Now, a heat source at 1200 Kelvin loses 2500 kilojoules of heat. So there is one source which is at 1200 Kelvin, and this is losing heat of 2500 kilojoules, and this heat is received by a sink. This sink is at 800 Kelvin. Next, there is second case, heat source is at 800 Kelvin. Okay, this is at 800 Kelvin, and again it's giving 2000 kilojoules of heat to the sink. This is at 500 Kelvin. Now, which of the following statements is true? Process 1 is more irreversible than process 2. Process 2 is more irreversible than process 1. Irreversibility associated in both the processes is same. And what is this? Both the processes are reversible. So definitely one thing, heat transfer between finite temperature difference is not reversible. So anyhow, this option, oh sorry for this. So anyhow, this option, sorry, we moved ahead. Okay, so this option, if you see, is not correct because heat transfer is occurring between finite temperature differences. So obviously, so both are not reversible processes because both are heat transfers between two temperature different bodies. So if you want to calculate delta S for the first process, see, this delta S for the first process is nothing but entropy change of this source plus entropy change of this sink. So if you calculate delta S of 1200 Kelvin body plus delta S of 800 Kelvin body. Now, if you see delta S of this 1200 Kelvin body, 2500 kilojoules of heat is coming out of this system. If heat is coming out, it is heat rejection by this 1200. So as a result, some entropy decreases. So minus 1200, minus 2500, because 2500 is the heat that is transferred. So minus 2500 divided by 1200, because these are sources and temperature remains constant. So from this integral del Q by T term, I can always take T out, because these temperatures remain constant. Now, plus whatever the heat this is getting transferred here, obviously this sink will accept that heat. Correct? See here. So if you cancel these two values, we have, if you take 25 common, we have 1 by 8 minus 1 by 12, which is something like, if you take out 4, then 1 by 2 minus 1 by 3, so 1 by 6, 25 by 12 minus 8 is 4 cancel this 2 times, this is 24 kilojoule per Kelvin. So this is the total entropy change in this process. Next, if you go for second process where heat transfer is occurring between 800 and 500 Kelvin temperatures at 2000 kilojoules, so delta S for process 2 for second process is equal to delta S of body at 800 Kelvin plus delta S with body of 500 Kelvin. Okay, something 1.04. Okay, let it be. So this is equal to, now see, this 800 Kelvin source is losing 2000 kilojoules of heat. So minus 2000 kilojoules divided by, this is at 800. Now whatever the heat this source is losing is collected by the sink. So 2000 divided by 500. So if you compare these values, so if you take, again, if you cancel these two zeros, so if you take 20 common, you have minus 1 by 8 plus 1 by 5. So this is equal to 20 into 1 by 5 minus 1 by 8 will give you 3 by 24. So this is 60 by 24. Correct? What is 1.5? This one? Okay, so anyhow, if you see, this is 60 by 64 and this is 25 by 24. Of course, this is also in kilojoule per Kelvin. Now, out of these two processes, in which process entropy change is more? Yeah, this is 1.5 basically. If you cancel 12 table, you will get 5 by 2. Acha, this is 40, right? If you take LCM, sorry, this is 40. Because the LCM, if you consider, this is 40. Yes, sorry, this is 40. So this is 1.5 kilojoule per Kelvin. Small issue with calculations. So this is 1.5 kilojoule per Kelvin, correct? So if you see, delta S in first process is equal to, if we assume reversible heat transfers, we are assuming. So in first process is 25 by 24, which is almost equal to 1 kilojoule per Kelvin. And delta S for second process is equal to 1.5 kilojoule per Kelvin. So now if you see, which is the process in which entropy change is more? So please tell me now, out of these first two processes, where first process is the sink at 1200 is giving heat and 800 is collecting, and in the second process 800 Kelvin source is giving heat and 500 Kelvin sink is collecting heat. Now out of these two processes, you see entropy change is more here, which means second process more entropy change, correct? So this implies entropy change is more in second process. So this implies process 2 is more irreversible. Process 2 is more irreversible than process 1 when compared. So if you see the things, process 2 is more irreversible than process 1, option B. Okay. So just calculating total entropy of the process that is involved with heat transfers. Okay. Yes. See, Vamsi, I'm telling you one thing. We calculated this assuming irreversible things. But normally, if you see, I told you entropy change if process is not mentioned between 1 to 2. Let us suppose a gas is changing its state from 1 to 2. If process is not mentioned, you can take any of the process because entropy is a point function and it depends only on the points. So if you see, if delta S along 1 2, which is reversible, is also same as delta S, which is according to irreversible. Okay, so I compared entropy changes that are involved here. Okay, in both the process. So we'll go for next question. So see, there is something it's given in an experimental setup. A flows between two stations P and Q adiabatically. Okay, adiabatically means there is no heat interaction to this fluid to this A between P and Q. Then the direction of the flow depends upon the pressure and temperature conditions maintained at P and Q. The conditions at P are 150 kilopascals and 350 Kelvin. The temperature at station Q is 300 Kelvin. The following are the properties pertaining to air: Cp value, Cv value, and R value. Okay. Of course, we treat air as the ideal gas. So enthalpy is just Cp into temperature, and internal energy is U is equal to Cv into temperature. So if this is the case, we'll see how things goes on. So basically, if you see in an experimental setup, this is station P and this is station Q. And some A is flowing from P to Q adiabatically. If this is flowing adiabatically, which means there is no heat interaction from this workstation or from this experimental setup to the surroundings. Now, let us go for the conditions. Of course, the direction of the flow depends upon the pressure, temperature conditions maintained at P and Q. Okay, the conditions at P are 150 kPa and 350 Kelvin. Okay, so pressure is P at P is equal to 150 kPa and temperature at P is equal to 350 Kelvin. Okay, next. Next. The temperature at Q is 300 Kelvin. Okay, the temperature at Q is 300 Kelvin. Okay, next. If the air has to flow from P to station Q, okay, we assumed the correct direction. So let us suppose A is flowing this way. Okay. Then the maximum possible value of the pressure in kilopascals at station Q is close to, so PQ max. This is what they want. Correct? What could be the maximum pressure at this Q? That's what the question it's given. So now see carefully. If you want the maximum possible values, means if you want the maximum pressure, if the pressure drop has to be minimum, the process has to be reversible. So delta S of the system, if you calculate, this should be equal to some finite value. Correct? Now it's given 150 and it's 350 and it's 300 and it's PQ max. So now if you see carefully, gamma is already given, which is the ratio of specific heats, which is 1.4. Basically, if you calculate the ratio, we'll be getting 1.4. Now this is an adiabatic flow. Now if the pressure has to be maximum, then what should happen? Obviously, this should be a reversible adiabatic process. Correct? Means basically the flow process which is happening should be reversibly adiabatic. So let us do that. Now, if you do this, see, pressures you're not known about that, but temperatures at both the cases. So if you see carefully, the maximum possible value of the pressure in kilopascals at station Q. So if you see, we have the relation between pressure and temperature for a reversible adiabatic process. So please apply that and tell me the answer. What could be the maximum possible value? Yeah, isentropic case. So please, by assuming whenever, of course, if pressure drop has to be minimum, the process has to be reversible. So for reversible adiabatic, because there is no heat interaction to the system from anywhere outside. So for reversible adiabatic process, you can apply PV power gamma is equal to constant, TV power gamma minus 1 is equal to constant, and also the relation between pressure and temperatures. So if this is the case, so please tell me what is the PQ max. 87.45. Is that what you are getting? Okay. So let me apply the relations. I have T V power gamma minus 1 is equal to constant. So in place of V, if I substitute T by P, So T by P whole power gamma minus 1 is equal to constant. So which means you can write T1 power gamma into P1 power 1 minus gamma is equal to T2 power gamma into P2 power 1 minus gamma. So this implies initial temperature at station P is 350 Kelvin. So 350 power 1.4. Okay, let us take this gamma common for all the expressions. So finally you want PQ. So let us enlarge this expression a bit in the next slide. So T1 P1 power 1 minus gamma. Okay, so see here we have T1 power gamma into P1 power 1 minus gamma is equal to T2 power gamma into P2 power 1 minus gamma. Correct? So now if you apply this, you want P2 because you need the pressure maximum possible at station Q. So P2 can be written as T1 by T2 whole power gamma by 1 minus gamma into P1, which means here in our nomenclature maximum possible pressure at station Q is equal to Tp by Tq whole power gamma value is 1.005 is divided by 0.718, which could give you 1.4. 1.4 by minus 0.4 into P1 is 150 kPa. So perform this calculation. Tp temperature, where is this? Okay, so see here. Let us look for the temperatures in the conditions. 350 at Tp and 300 at Tq. So this is 350 and this is 300. Whole power minus 0.4, I mean minus 1.4 divided by 0.4 into 150. So please calculate this value and tell me what could be the answer. If you cancel 50 table, this is 7 times, this is 6 times. So PQ is equal to 7 by 6 whole power. This is minus 7 by 2. You can write into 150. So please calculate this value and tell me what could be the answer for this. Or let me calculate 5 by 7 by 6. This is the calculator. Okay. So 7 by 6 whole power, yeah, here is the power, minus 7 by 2, because 14 by 4 could give me something like this. This into 150 kPa, so 87.45 is the answer. So if you write this, we have 87. So we have 87.45 kilopascals is the maximum pressure that could sustain without any heat transfer to the surroundings. So did you all understand how this is 87.45? Clear? Because pressure drop, if there is some friction, there will be some energy of the fluid that is spent in overcoming the frictions. Correct? So as a result, if total energy of the fluid decreases, Bernoulli's theorem in fluid mechanics very well, and here air is also a fluid. If there is friction, there will be some frictional losses when it's flowing through the passes. But if the pressure drop has to be minimum, means if the maximum pressure has to be maintained at the other end, then definitely your process has to be reversible, which means there should not be any irreversibilities like friction. Okay, and if the process is given adiabatic, and if you assume reversibleness for getting the maximum pressure at the other workstation, then the process has to be reversible adiabatic, and you can apply this equation for reversible adiabatic process. Clear to all of you? So the correct answer for this is something it's given 87 here. Okay, close to that, 87.45. Yeah, we can use see, basically this comes from the entropy formula. Correct? You can also use for a reversible process, isentropic process, ds is equal to 0. So if you equate again, you will be getting the same expression, t p power 1 minus this expression basically. You can ask for any number of Ajay, no issues, they'll keep on giving you. But this is a simple calculation. See, if I myself solve this question, after writing this equation, I'll put this only 2 steps. But since I am in a class now, so I want people to understand. So we are elaborating it step by step. Okay. Yeah, we have Cp and R values given. Here, Cp is given, R is given. You can apply. See, I'll show you if you are, a bit confused with this. So delta S is equal to, see, you want the relation in temperatures and pressures, correct? So if you want the relation in temperatures and pressures, minus R ln P2 by P1 plus Cp ln T2 by T1. This is what is with you. Correct? Now see carefully. If this is 0, if I bring this R ln P2 by P1 here, so this implies R ln P2 by P1 is equal to ln Cp ln T2 by T1. Correct? This is what we have. So now if you see this R, which is in the multiplication to this P2 by P1, can be written on the top. So ln P2 by P1 whole power R is same as ln T2 by T1 whole power Cp. So if you remove this ln on both sides, you have P2 by P1 is equal to ln T2 by T1 whole power Cp by R. And you know Cp by R is nothing but gamma by gamma minus 1. Okay. You'll get the same relation again. So you can use any of these two, no matters. Both gives the same things. But since we directly know for reversible adiabatic process, this is the governing equation we can apply because we have temperatures and pressures. Okay. Both are same. Clear? No, never go for blind things. Just apply the physics that's governing here. You know, if there is some irreversibility, then energy of the fluid decreases, so pressure decreases. But if you want the maximum pressure at the other end, there should not be any irreversibility that's happening within the system. So you can use maximum amount of work. Okay. This is the question. So if you see, if the pressure at station Q is 50 kPa, the change in entropy SQ minus SP. So this time they have given P1 is equal to 150 kPa and T1 is equal to 300. How much did they give you? Something else. Tp is 350 Kelvin. Okay, so here the temperature is also 350 Kelvin. And here at station Q, the temperature is 300 Kelvin. So if P2 is 50 kPa, means the process is not reversible, because if process is going reversible, we have seen just now the maximum value of P that we can get is 87 around, correct? But here if P is not 87, that means there is some irreversibility that is lying within the system, correct? Because the maximum that's possible to get here is 87 kilopascals, but it's given only 50 kilopascals, which means the process is not completely reversible. There is some irreversibility that is lying within this. So if you apply this entropy change equation, because the entropy change between the same states for irreversible process is also same as delta S for the reversible process. Of course, heat interaction wise it's different, but if you see, entropy is a point function. So either the system goes from this point to this point in a irreversible path or a reversible path, the entropy will be same. So now if you want to calculate the entropy, since we can assume air as an ideal gas, we have expression just now we wrote. So reversible is equal to Cp ln T2 by T1 minus R ln P2 by P1 for ideal gas. So if you apply, Cp is given. Answers are in kilojoule per kg Kelvin. Fantastic. So Cp in kilojoule per kg Kelvin is 1005 something. It's given here in the data initially 1.005. Okay. So 1.005 into ln T2 by T1. T2 is 300. T1 is 350. So 300 divided by 350 minus R value 0.287 into ln P2 by P1. So P2 is 50 and P1 is 150. So this is 50 by 150. So please calculate and tell me what could be the value in kilojoule per kg Kelvin. See, just basics. We are applying only basics. Nothing rocket science involved here. Simple. We know we deduced all these formulas, and complete story is running only on one equation. Correct? So please tell me what could be the answer for this. This is 6 times. This is 7 times. And this fellow cancels this 3 times. So punch your keys and tell me. No, for irreversible process, who told entropy is negative? It can be more positive actually. There is a chance for that. For irreversible cycle, integral del Q by T is less than 0 as per this Clausius equation. Clausius inequality. Vijay Sai, see carefully. Delta S is equal to cyclic integral del Q by T plus S generation, correct? Now suppose if the process is irreversible, this term anyhow it's positive. Now if you add heat to the system, this term can also be positive. So positive plus positive will be positive and total entropy increases. So there can be a chance. Okay, Vijay Sai, clear? See, don't get confused. Entropy can always increase or decrease, or it can remain constant in a process. No matters. Okay, so what would be the answer for this? Please calculate this. 1.005 into ln 6/7 minus 0.287 into ln 3. So please 1.6 or 0.16. 0.16 Rohit. So this could be the correct answer. That's what you are telling. Okay, let me calculate the value. Okay, now let me see whether it's 0.16 or not. Let me calculate. This is ln 6/7. Okay, so see here. Let me use a calculator and calculate the values. So if you see here, 1.005 into, now you want 6/7 log value. So 6/7 and you apply ln for this. So ln of this value is of 6/7 into 1.005. This is the total value. Now to this we need 0.287 into ln 3. So plus 0.287 into ln 3 value. 3 times of this ln will totally give you 0.1603. See, I used ln because I used plus sign here. Actually here, here we have minus of log 1/3. So if I use this as log 3, you can change this as plus sign. Vamsi, whenever I am using pressure ratio, it's Cp here. So please check. In the formula that we deduced, 0.16. See, Vamsi, see carefully. In the formula that we deduced in last class, we have Cp ln T2/T1 minus R ln P2/P1. Whenever we have pressure ratio here, we are using Cp here. Okay. So this is total delta S for a reversible process. Since entropy is a point function, whether the process gets carried out reversibly or irreversibly, total entropy change from this between these 2 points is same along all paths. So this delta S along reversible is also same as delta S along irreversible. So to get this station Q at 50 kPa, the total entropy change SQ minus SP is 0.160. As we know, there is some, even though there is no heat loss outside to the system, but since we know by somehow the maximum possible pressure is 87 kilopascals, but only 50 kilopascals is the exit pressure, which means some pressure energy of the fluid got lost because of some irreversibilities, and this is an irreversible process, which means even though you don't have any energy interactions, heat interactions, basically your entropy is increasing by small amount. Because of what factor this entropy is increasing? Can anyone tell me? See, this process is irreversible, because the maximum outlet possible pressure is 87 kilopascals, but you got only 50 kilopascals. Means that this process is not reversible. But if there is no heat interaction to outside or within the system, can you tell me how there is some increase in entropy? Because this is due to entropy generation that is happening during this irreversible process. Okay, clear? Because delta S of an irreversible process at the end should be equal to 2 things: del Q by T within the process plus S generation. But in this case, process is adiabatic, no heat is going out of the system. So if this term is 0, this should be equal to this, and this value you got it as 0.16 kilojoule per kg Kelvin. And this increase in entropy from P to Q is because of the pipe friction that is happening, and that is due to entropy generation that's happening in this process. Clear to all of you? Did you all understand this? Why entropy is increasing? Actually, you should get a positive value here. If you get negative value, you should check your answers, because the process, there is no heat interaction to the system, which means this term is 0 plus S generation, and S generation is always positive, which means the total entropy change for the fluid to transfer should be positive. Understood? Clear to all of you now? Can I move for the next question? Okay, if that's fine, then we'll move for the next question. Yeah, this is the next question. An ideal gas of mass M and temperature T1 undergoes a reversible isothermal process. This fellow has to be recognized. Reversible isothermal process from an initial pressure P1 to final pressure P2. Okay, it's nothing given, it's expansion or compression. Okay, fine, but some isothermal process. The heat loss during the process is Q. The entropy change delta S of the gas. So see here, we have the formula for delta S of the gas or the system is equal to, let me remove this G here. of the system is equal to, see, it's given ideal gas. So when we are dealing with ideal gas, of course, if we are assuming constant specific heats, then tell me this delta S of the system is given as Cp into ln T2 by T1 minus R ln P2 by P1. Correct? This is what we have. Now, in the question, it's mentioned the process is isothermal. If process is isothermal, means if temperature is constant, this implies T2 by T1 is equal to 1. So log of this T2 by T1 will be 0. Option B is correct, Uganda. Okay, let me check. So this term, it goes for 0. Okay, next. Delta S of the system is equal to minus R into ln P2 by P1. Okay. The heat loss during the process is also Q. Okay, the entropy change delta S of the gas. So if you see minus R ln P2 by P1. So this R you can always replace with, okay, since this is for specific terms, if you want total capital change of S, this should be multiplied with M, because obviously we are dealing for specific entropies, because you know we are putting R, Cp and kilojoule per kg Kelvin and all. So if you want total entropy change, you will need to multiply this with mass. So minus M times of R into ln P2 by P1. Okay, and yeah, if you take this minus, then you'll be getting M times of R into ln P1 by P2. So this implies total entropy change of the system is equal to this. Okay, B is the correct answer. Pamsi, please take care of this minus sign. Okay, there is one minus sign here. It's not plus. I think you missed this minus, so you might have got this A, but there is some minus sign difference. Now, don't get confused because of this Q by T term. Okay, this Q, whatever the entropy change that is there because of this heat transfer is already included in this. Okay, because we are finding the entropy change between two states. Okay, so whatever might happen between the two states doesn't matter. Since entropy is a point function, it depends only on the initial and final points. Your entropy change has already taken this heat transfer into the account here. Okay, so MR into ln P1 by P2 is the answer, which is present in option B. Clear? Vamsi, I hope you missed this minus sign here. So if you don't miss this minus sign, you can get the things. Understandable to all of you? Option C is for universe. For C to be universe, you know, first of all, there should not be heat loss to get minus sign here, because if heat is added to the universe, you know, when heat is added to a system, it is considered positive, and if the universe is, I mean, if the surroundings is also at T1, then you'll get this T1, Q by T1, which is as the entropy added to the universe because of this heat transfer. Okay, because if heat is added at constant temperature, then you'll be getting Q by T as the entropy change, and if heat is added, you'll be getting positive. So if there is a plus sign here, and if the surroundings is also at a temperature T1, then this could be the entropy you're asking for universe. So clear? This is option B. Nothing difficulty here. So let's go for the next part. Okay. See this question. An amount of 100 kilowatts of heat is transferred through a wall in steady state. So see this question carefully. It's given the heat transfer is occurring at steady state. One side of the wall is maintained at 127 degrees Celsius and the other side is maintained at 27 degrees Celsius. The entropy generated due to heat transfer through the wall. It was asked in GATE 2014. So see here. There is a wall initially. Okay. There is wall, and you know this side of the wall is maintained at 127 degrees centigrade. So T1 is equal to 127 degrees centigrade, which is of course in absolute scale of temperatures, this is 400 Kelvin. Okay. Now 100 kilowatt of heat is transferred through the wall. So let us assume if this is 100 kilowatts of heat that is flowing in. Now see carefully, it's given this wall is in steady state. Means if I ask you what's the amount of heat that should come out, what is your answer? See, it's given its wall is in steady state. So if 100 kilowatts of heat is going in, and if I ask you if this wall is at steady state, then how much heat should come out? What could be your answer? If you apply energy balance in steady state, please respond. If 100 kilowatts is going in, what's the power that should come out of this wall? Same, correct? Because whatever energy that is flowing in, it should come out at the end. So this is also 100 kilowatts. because this wall is in steady state. So if this is in steady state, and let us suppose S dot gen is the entropy generation rate inside. Now this is our main point of interest. Correct? This wall, what we are talking about. Now see carefully. We can write S dot in minus S dot out plus S dot generation is nothing but delta S dot of the control volume. Correct? If you write entropy balance, whatever the entropy that is coming in plus whatever that is getting generated within the inside because of some irreversible heat transfer minus whatever is going out, that should be equal to total entropy that is getting stored within this system. So if you see, if this device, if this wall is at steady state, then will there be any change in its properties? No, which means the change in entropy of the control volume is 0. Correct? Did you all understand why I have equated this delta S at control volume to be 0? Because the wall is running under steady state, which means the properties of the wall doesn't change with respect to time. So if you are talking about rates, there is no change with respect to time. So which means this delta S dot will be equal to 0. Now, what could be the answer? S generation within the wall is equal to entropy that is getting out of the wall minus entropy that is getting transferred into the wall. So now if you see, what are the exit temperatures given? And on the other side, the wall is at 27 degrees centigrade. So T2 is equal to 27 degrees centigrade. And this implies T2 is equal to, now 273 plus 27 will give you 300 Kelvin. So this is the case. And now see carefully. 100 kilowatts is added to the surroundings, which is at 300 Kelvin. Means this face of the wall is at 27 degrees centigrade, and the heat that is causing this 27 degrees centigrade wall is 100 kilowatts. Similarly, the heat that is causing this wall, which is at 127 degrees centigrade, is also 100 kilowatts. So if you talk about entropy that is going out and in, so we have S dot generation is equal to S dot out minus S dot in. So now if you want this, since temperatures are constant, we can take out the temperatures. 100 divided kilowatts divided by exit temperature is 300 Kelvin minus S dot in. This is also 100 kilowatts because the power that's entering the wall is also 100 kilowatts and the entry temperature is 400 Kelvin. Okay, so now if you cancel the zeros as well. Okay, so if you cancel the zeros, we have 1 by 3 minus 1 by 4 kilowatts per Kelvin is the entropy that is getting generated inside the system. So if you can see the things, 1 by 12 kilowatts per Kelvin. But if you see the question, in the question it was asked watts per Kelvin. So this is equal to 1000 divided by 12 watts per Kelvin. So if you cancel the things, 4 table could be 3 times and 4 table could be 250 times here, and 3, when you cancel 3, 3.33. So if you see, entropy generation rate S dot gen is equal to 83.33 watt per Kelvin, and this is the rate in which entropy is getting generated within the wall because of heat transfer due to finite temperature difference between the two faces of the wall. Okay, so 83.33. See, you need to take care of these units, okay? Because if you write this answer in kilowatts, like 0.833, your answer goes wrong, correct? So you need to take care of the units very well, and you need to write the things. Is there any big thing that is difficult here? No, just it's an entropy balance equation, and we are done with the question. See how easy the entropy is. Clear? Understandable to all of you? Please respond yes or no, depending on situation. And you can see, this is a simple calculation which doesn't even require a calculator first. So next, I'm going for the next part of the question. Okay, a closed system contains 10 kg of saturated liquid ammonia at 10 degrees centigrade. Heat addition required to convert the entire liquid into saturated vapor. For the time being, I didn't talk about saturated liquid and saturated vapor because we are going to talk well about this in next lesson called properties of pure substances. But till then, I would like to recall one general point which during phase change of any pure substance, means for example, if you are heating ice, if you are heating some other pure substance generally, during its phase change means by the time the complete liquid on supplication of some heat will get converted to complete vapor because of this fellow heat that you are supplying. Now, during this phase change process, liquid phase and solid phase and gaseous phase are the three phases generally. So, generally when you are supplying some heat, the substance which is in liquid phase gets converted to vapor phase. During this phase change process, both temperature and pressure remains constant for a pure substance. Okay, and let us treat, since we are given only ammonia and we are not given with any other mixture with this, we can treat ammonia as a pure substance, which means when you are supplying some heat to a pure substance, and because of this application of heat, if phase is getting changed, definitely temperature and pressure remains constant. This much you need to understand to solve this question. If you know this, which is generally known to you in your material science course, you might have learned this point. So a closed system contains 10 kg of saturated liquid at 10 degrees centigrade. Heat addition required to convert the entire liquid into saturated vapor at constant pressure, of course phase change is at constant pressures generally, is 16.2 megajoules. So 16.2 megajoules of heat has to be supplied. If the entropy of the saturated liquid is 0.88 kilojoule per kg Kelvin, the entropy of the saturated vapor. So see here, saturated liquid, okay, let us not use this word. So see here, entropy of saturated liquid and entropy of saturated vapor. This is what you want. So this is state 1 and this is state 2. Now, during the system goes from, during the system changing its phase, it goes from state 1 to state 2. And I told you for phase changes, temperature is constant, which means, can I write S2 for saturated vapor minus S1 for saturated liquid is equal to integral Q by T, and temperature is constant, so we can write this temperature is constant and it's given 10 degrees centigrade, so this is 283 Kelvin. And what are the heats that is supplied? 16.2 megajoules. And finally he's asking value in kilojoule per Kelvin, kg Kelvin, and this is also given in kilojoule per kg Kelvin. So let us convert this megajoules into kilojoules. So if you convert this megajoules into kilojoules, we have 1620. I think one more zero could add here, kilojoules. Just a second, some issue with this. Okay, so this is in, of course, so this is in kilojoules. Okay, I think this corner is not supportive, so let us change the things here. Okay, so if this is not working out, we'll write it in the next slide that we have. So see here, S2 of saturated vapor means basically at state 2 minus at state 1 for saturated liquid is equal to, the heat that is exchanged is 16200 divided by 283. This is in kilojoules and this is in Kelvin. And of course, you can also see total amount of mass that is here is 10 kgs. So if you want to write in kilojoule per kg, we need to divide it with 1 by 10 kgs. So total you have 1620 divided by 283 kilojoule per kg Kelvin change of entropy for this process. Okay, so now if you want it at state 2 for saturated vapor case, you can always write this entropy of the saturated liquid is given in kilojoule per kg Kelvin, which is 0.88. So 0.88 plus 1620 divided by 283, and this total is the value in kilojoule per kg Kelvin, where this value is the entropy change of, entropy of the saturated vapor that is with us. So please calculate this value and tell me what would be the answer. Or shall I do this? 1620 divided by 283. So if you see 1620 divided by 283 plus 0.88, 6.60. 6.60. This is ridiculous today. Okay, so see here 6.60 kilojoule per kg Kelvin. Yeah, correct. Vamsi, Uganda, all of you. So this is entropy of the saturated vapor. Okay, are options given to this question? No, but 6.6 is the correct answer. Okay, so clear, there is nothing big here. Just we have, since temperature is constant, we wrote Q by T directly. Okay, because during phase change process, temperatures are generally constant. So now 10th question. 1 kg of A undergoes an irreversible process between equilibrium states 1 and 1 is at 20 degrees centigrade and 0.9 meter cube, and equilibrium state 2 at 20 degrees centigrade and 0.6 meter cube. The entropy change in the process means it's given a gas is undergoing between two states, undergoing a process between two states, and the process is irreversible process. But to calculate the entropy change here, nothing like entropy generation or heat transfers are given, only states are given. So how to calculate this? You know, suppose if you plot this on a T versus volume axis, the system is going something like this, correct? Because temperature is same, but volume is changing. So okay, let us not assume this because it's not given, it's isothermal. So see here, only these are the two states we can talk about, 1 to 2. Okay, now a gas is executing a process between states 1 and 2 for which path is not given to us, but please tell me delta S along the process 1 to 2. If I consider it along path A and if I consider this along path B, along A and along B, can you tell me what mathematical sign could fit in between? Equal to or less than or greater than? Between these two, please tell me, between these two terms, which mathematical sign could fit here? Equal to sign or less than sign or greater than sign? Equal to sign, because entropy change depends only on points. So this is the first point and this is the second point, basically initial and final states. So this is here. So if you can assume it's undergoing a reversible process, means entropy change along reversible is all between 1 to 2 is same as delta S along irreversible along 1 to 2. Correct? So since if we assume a reversible process is taking place, it's given A, so we can assume this as an ideal gas, and we know 20 degrees centigrade and 0.9 meter cube and 20 degrees centigrade and 0.6 meter cube are the two states. So if you calculate this value, we have for ideal gas undergoing a reversible process, we know the formulas. Correct? So let us apply. For a reversible process, undergoing a reversible process, this delta S is equal to Cp ln, I think volumes are given. So let us use formula in terms of volumes and temperatures. Cv ln T2 by T1 plus R ln V2 by V1. Okay, so if you see this T2 by T1 log term is 0, because if you see initial temperature is 20 degrees centigrade and final temperature is also 20 degrees centigrade, which means both initial and final temperatures are same. If both initial and final temperatures are same, this T2 by T1 value is 1. And for A, you can take this as 0.287 into ln V2 is 0.6 and V1 is 0.9. So you can calculate this value simply and you'll be getting the answer in kilojoules per kg Kelvin, because this R we are substituting is in kilojoules per kg Kelvin. So let us calculate this value. 0.287 into ln 0.6 divided by 0.9. See, 0.287 into, now you want 0.6 by 0.9 value when applied to the log. So open a bracket, 0.6 divided by 0.9, close the bracket, and apply logarithm. So you can see 0.287 into ln of 0.666 is minus 0.1163. So minus 0.1163. So now if you make the things a bit clear, how much is the answer that we got here? Minus 0.1163, correct? Kilojoule per kg Kelvin. Now, if you see the question carefully, in question it was asked joule per kg Kelvin. So, if you convert this kilojoules into joules, let us write this a bit close. Acha, this won't go up, but this will go, correct? So, minus 0.116 is what we have. So, if you write this in joules, 11.6 kilojoules per, joules per kg Kelvin. This is what the total entropy change between states for the process 1 to 2, which is S2 minus S1 basically. Okay, and since you know delta S along reversible process for process 1 to 2 is same as delta S along irreversible process along 1 to 2, this implies delta S of irreversible process along 1 to 2 is equal to minus 11.6 joule per kg Kelvin. Okay. Acha, sorry, correct. This is 116. Correct one thing, because you know minus 116.36 into 1000 will give you minus 116. So correct. Did you all get minus 116 for this? It's a very simple question we can do. The only thing you need to know is by seeing the word irreversible in the question, you shouldn't get panicked, because you should know whenever initial and final states are same, the entropy change calculated either by reversible process or by irreversible process, both are same. Okay. So this is the next question. So please try to solve. 1 kg of ideal gas constant R is equal to 400 joule per Kelvin. It is specific gas constant because the units are in joule per kg Kelvin. Okay. Specific heat at constant volume is 1000 at 1 bar and 300 K is contained in a sealed rigid cylinder. So there is one sealed rigid cylinder. Okay. Let it be. Okay. Let us suppose it's not adiabatic or something. Okay. Doing an adiabatic process is given. So let us keep this drawing like this. So now see here. Let us change some color and let us write things. This is rigid container. And of course sealed. So volume is always constant, because whatever mass that is there, that is constant, and volume is also constant. Now 1 kg of ideal gas. Okay, there is 1 kg of ideal gas that is sitting here. Now characteristic gas constant and okay, properties are given, characteristic gas constant and CV values are given at 1 bar and 300 Kelvin. This is the story. So P initial is equal to 1 bar and T initial is equal to 300 Kelvin. Okay. Next, during an adiabatic process, 100 kilojoules of work is done on the system by a stirrer. So if you see carefully, there is one stirrer within this. So what happens? There is some rotation, and whenever this is getting rotated, because of the friction that is present here, some portion of heat will get added to the system. Let us use a different color to show this. So some portion of heat will get added to the system because of the friction between these two fellows. So I told you entropy doesn't get transferred through work. Means if you see the system boundary here, entropy doesn't get transferred. Yes, even now I will tell you entropy doesn't get transferred, but entropy can be generated. Understood? Because of the interaction between the physical things that are present, entropy can get generated when you transfer work, but entropy which is outside the system can't be transferred inside. Okay, like how we have in case of mass transfer. If there is some mass transfer into the system, then you can transfer some entropy into the mass, or else if you are supplying some heat. But when work is crossing the boundary, entropy is not getting transferred at this point. But whenever your work is transferring to the system, because of the friction and all, your entropy can get generated. There is some source. Now, work is done by the system, by stir, the increase in the entropy. Okay, so see here. Delta S means basically you want to calculate what's the value of this delta S of the system. So delta S of the system is equal to, see carefully. Tell me one thing very carefully. If this paddle wheel or stirrer is doing 100 kilojoules of work, what's the heat that is transferred to this? I told you work can be completely transferred to heat. Correct? Heat can't be transferred to work completely because there will be some losses as per Kelvin-Planck statement. But work, whatever is available, can be completely transferred to this, completely transferred in form of heat. So if you do that, see, the initial conditions are 1 bar and 300 Kelvin. Now, CV is given to you. Okay. Then what is the entropy change? So to calculate entropy change, basically you need to write Q by T. Of course, integral del Q by T, for example. Now, how to get the expression for del Q in terms of T? This fellow helps you. It's given container is rigid. So if you apply first law of thermodynamics, del Q minus del W is equal to du. So whatever the work that it is having can't produce any displacement work here, and only input, because of this friction, it's getting converted to heat. So du can be written as del Q, and for ideal gas, this du is equal to Cv dt. So here we can write integral Cv dt divided by T. Okay, so now see carefully. It's given, the initial conditions are given, means 1 bar and 300 Kelvin is given. Now they are asking you for the increase in entropy of the system, but this entropy, this temperature changes. So if you see carefully, what's the total change in temperature? Whatever the energy that you are supplying, 100 kilojoules is equal to Cv, 1000 into delta T. But of course, since this delta U is in kilojoules, we will convert into 10 cube. So this 10 cube gets cancelled. So delta T is equal to 100 Kelvin. So final temperature that you will be getting is T final is equal to 100 plus T initial, which is equal to something like, initial conditions are 300 Kelvin. So final temperature will be 400 Kelvin. Means during this heat addition process, the entropy of the system gets changed, and because of this, temperature will go initially from 300 Kelvin to 400 Kelvin. Correct? So you can put that here. So we can calculate the values. Please calculate. Cv is given. You know the formula. So please calculate the value and tell me. This rigid container analysis is given to know the final temperatures. Okay. So please tell me this value. Cv is with you. T is known to you. 287. And I think this should be in joule per Kelvin, if I am not wrong. Correct? Yeah. Joule per Kelvin. Obviously it increases because it's an ideal gas which is closed. So definitely when temperature is increasing for ideal gas, if volume is constant, then definitely pressure increases because PV is equal to RT. So if your volume is fixed and if your T is increasing, then definitely P should increase to satisfy the equation. Correct? So this is 287. Okay. So next, try to solve this. 1 kg of an ideal gas, R value is given, undergoes a reversible process from 1 bar 300 Kelvin to state 2 at 2 bar 300 Kelvin, the change in specific entropy. This question is very similar to the one that we solved just ahead. So please solve this question and tell me the answer. What could be the answer, all of you? But the process is not reversible, Vamsi. Correct? Okay, maybe because of this expression you're asking that. See here, this actually this entropy change is because of this heat that is added here. We are considering gas as this system, okay, not this completely. Let's have it. Okay, so if you get a bit confused, we can remove these things and we can write always, this is equal to, you can apply this formula basically. So temperature is increasing, volume is constant. So if temperature is increasing and if volume is constant, you can apply Cv into ln T2 by T1, which is the same thing that we have. Same expression, Cv ln T2 by T1. So if I write this directly, I think your doubt might get cleared. Correct? So Cv is 10 cube into, this is ln 4 by 3, 400 by 300 basically. Okay. So this, what's the answer for this? 1 kg of ideal gas at gas constant is undergoing an irreversible process from state 1 from 1 bar 300 Kelvin to 2 bars 300 Kelvin. The change in specific entropy of the gas in the process is dash. Simply apply, the two states. So you can apply, since for irreversible process or irreversible process, this S2 minus S1 remains the same because S is a property. So delta S remains the same. So delta S is equal to, since pressures and temperatures are given, you can write minus R ln P2 by P1 plus Cp ln T2 by T1. So if you see, this term is 0 because this temperature is also 300 Kelvin and the state 2 temperature is also 300 Kelvin. So minus R ln P2 by P1. And P2 is 2 bar and P1 is 1 bar. So 2 by 1, which is equal to minus 0.287 into log 2. You can calculate this value. Whatever it gives you, that's the answer for this. Minus 0.287 into ln 2. And of course, they are asking in joules. So 287 into ln 2 joules per kg Kelvin. Because anyhow, it's given 1 kg. So calculate, of course, with a minus sign. So please calculate this and tell me the answer. Minus 287 into ln 2. Let us calculate the value. Minus 287 into ln 2 will give you minus 198.9. Yeah, minus 198.9. Okay, so what's the answer? Minus 198.9 joule per kg Kelvin. Okay, so next, it's a very simple question you can do. So see here, again, I hope something similar is given. State 1, state 2s are defined. An ideal gas undergoes a process from state 1 to state 2. The specific heats of ideal gas are 1 kilojoule. 0.7 kilojoule per kg kelvins, the change in specific entropy. So please do this. Conditions are given, temperature and pressure are mentioned. So please do this. Same formula, delta S is equal to this time temperatures and pressures are given. So again temperatures and pressures. So minus R ln P2 by P1 plus Cp ln T2 by T1. This was asked in GATE 2018 for 1 mark. So this is equal to, so nothing is constant here, so we need to apply. If Cp is 1 and Cv is 0.7, then R value is 0.3 kilojoules. So minus 0.3 into ln P2 by P1. P2 is 500 and P1 is 100. So this is 5 plus Cp is 1 into ln T2 is 600 and T1 is 300. So this is 2. So this is ln 2 minus 0.3 into ln 5. You need to calculate this value in kilojoules. Of course, we dealt everything in kilojoules, and mass is given 1 kg. So anyhow, they are asking for specific entropy change. So specific entropy change from state 1 to state 2 in, we need to calculate for 2 decimals. So calculate this value, ln 2 minus 0.3 into ln 5. Let me calculate ln 2 minus 0.3 into ln 5. So ln 2 minus 0.3 into ln 5. Okay, 0.21. So if you calculate to 2 decimals, okay, anyhow this decimal is 0, so 0.21 could be a reasonably good answer. Okay, so 0.21 kilojoule per kg Kelvin is the entropy change in kilojoule per kg Kelvin. Okay, and this question was asked in GATE 2018 for 1 mark. Nothing difficulty here, it's a simple question that you could afford for. Then this, I think he's asking for the formula this time, and this was asked in GATE 2018 again. For an ideal gas with constant properties, means basically he means Cp and R are constants undergoing a quasi-static process. Of course, we assume this reversible for this ideal gas and we derive. Which one of the following represents the change of delta S from state 1 to state 2? This is the formula that we are applying since long. So Cp ln T2 by T1 minus R ln P2 by P1. This is the correct formula. But when temperatures and volumes are there, this should be R. It is not R, so this should be R actually. So that's why this is wrong. And finally, you know, we have Cp minus, we should not have Cv into R, we should have only R. So because of this Cv, this is wrong. And Cv ln T2 by T1, when ln volumes and temperatures are there, this should be plus, but because of this minus sign, this is also wrong. So correct answer is option A. Yeah, Uganda, please see there is a minus sign here. Okay. Clear to all of you? Can I go for the next question? It's a simple formula that we are applying since long. So this is the question. I think 1 or 2 questions are left with us because it's already GATE 2019 here. So please see, A of mass 1 kg. I think there should be one more yes here. A of mass 1 kg. Initially at 300 Kelvin and 10 bar is allowed to expand isothermally till it reaches a pressure of 1 bar. Okay. Assuming an ideal gas behavior with gas constants of 0.287 kilojoule per kg Kelvin, the change in entropy of air. So see here, there is A basically, which is, if you write this on a PV diagram, it's given expand isothermally, means the A is expanding isothermally. So if this is state 1, this is state 2. So there is isothermal expansion. By the time I mean isothermal expansion, this 300 Kelvin remains constant throughout and this mass is 1 kg. Okay. Next. So if these are the cases, till it reaches, initially pressure is 10 bar and final pressure is 1 bar. Assuming A as an ideal gas with constant of 0.287 kilojoule per kg Kelvin, change in entropy. Correct, Uganda. All of you, I am sorry for this. This option is also correct because this V1 by V2 is compensated with this minus sign. So both A and A are correct. We need to be careful with this plus and minus signs and T2 by T1, V2 by V1 values. Okay. So both A and A are correct here because this V2 by V1 is compensated with this minus sign. Correct, you can then. So see here. So delta S. If you talk about delta S, again we have Cp ln T2 by T1 minus R ln V2 by V1. I mean R ln P2 by P1. So if this is an isothermal process, this value is 0. So minus, they're asking in kilojoules. So let us put 0.287 into ln P2 by P1. So finally, the pressure is 1 bar and initial pressure is 10 bar. So 1 by 10. So this is equal to 0.287 into ln 10 to this whole multiplication in kilojoule per kg Kelvin. So basically 0.287 into log 10 is what you need to calculate to get this. So please calculate this 0.287 into log 10. 0.287 into log 10. Log 10. Okay. 0.66 is the answer. So 0.66 kilojoule per kg Kelvin. We'll go for one last question, I think. Yeah, GATE 2020. So please see here, this question was asked in GATE 2020 examination. So please see carefully. For an ideal gas, a constant pressure lines and a constant volume lines intersect at a point. Of course, we have seen for a TS diagram, if you see from process 1, let us suppose this is the point where one line is constant process and pressure and one line is constant volume. So out of this, if these are two lines, 1A, 1B, tell me out of this 1A and 1B, which is constant pressure and which is constant volume. I have told you this, and we have derived some important expression for slope of this process. You remember, we have derived this. Whoever is daily attending my class, they can tell now. So if you see, we have derived the slope for constant pressure process and constant volume process, and out of these two, one is constant pressure, one is constant volume. So tell me out of this 1A and 1B, which is constant volume. Okay, this is constant volume process and this is constant pressure process. And I told you why constant volume process lie above the constant pressure process. Correct? Rohit, it's correct. So see what he's asking for. Cp is the specific heated constant pressure and Cv is the specific heated constant volume on a temperature versus specific entropy diagram. Okay. The ratio of slope of constant pressure and constant volume lines means basically he's asking, I told you slope is dt by ds for constant pressure divided by dt by ds at constant volume. This is what he is asking for. Now, what's the slope of constant pressure line? What's the formula we got? You remember? We are deriving this last day. So, if you see, what's the slope of this constant volume process on constant pressure process on the diagrams? This is T by mCp and this is T by mCv. Correct? This is what we got as constant slope for constant pressure process and this is slope for constant volume process. So now if you cancel the things, Tt gets cancelled because at the point of intersection temperatures are same and mass gets cancelled. So we have 1 by Cp by 1 by Cv is nothing but Cv by Cp is the answer, which is in option D. Cv by Cp. Okay. I told you why this T by mCp and T by mCv are the values. Correct? We have derived something on the other day. If you look at notes, you can see the things. Temperature in this constant pressure process and constant, volume process, both are same. Correct? So we'll go for next question now. This is the last question, I guess. Yeah, this is the last question. So we'll calculate the values. 1 kg of A, it was asked in GATE 2020. This is the last question that we'll discuss today and we'll make a move. 1 kg of A in a closed system undergoes an irreversible process from initial state of 1 bar absolute pressure, of course, T1 is 27 degrees centigrade, to a final pressure of P2 3 bar and 127 degrees centigrade. If the gas constant is 287 joule per kg Kelvin and ratio of specific heats gamma is equal to 1.4, change in specific entropy. Can you calculate? See, where the gas is going from, if you try to draw this on a P versus T diagram, for example. Okay, let us draw this on a PT diagram. P, T, and this is state 1, which is at 1 bar and 27 degrees centigrade, and this is state 2, which is at 3 bar and 127 degrees centigrade. So if this is the case, there is some irreversible process that's happening here. But if the process is reversible or irreversible, that doesn't matter. Delta S between 1 to 2 is same along all paths. So again, pressure and temperatures are given. So we can calculate delta S. Delta S is equal to, along for the process 1 to 2, is equal to Cp ln T2 by T1. So Cp value is given here. It's given. Yeah, ratio is given and R is given. So we can calculate. If you calculate, you'll be getting 1005 approximately. So 1005 into ln T2 by T1. T2 is 127 degrees centigrade. So this is 400 Kelvin divided by 300 Kelvin minus R value 287 into ratio of pressures 287 ln P2 by P1. So P2 is 3 bar and P1 is 1 bar. Since we are talking about ratios, we can always substitute in bars as long as they are in same units. Otherwise, if you are substituting in ideal gas equation, we need to make this as 300 kilopascals and this as 100 kilopascals. So this is ln 3 by 1. So you can calculate it. 1005 into ln 4 by 3 minus 287 into ln 3. Let us calculate this value. 1005 into ln 4 by 3 minus 287 into ln 3. So let us calculate this. So 1005 into ln 4 by 3. So 4 by 3 ln. This is what we have, minus 287 into ln 3 minus 26.18. So let us see the values. So if you see minus 26.3, which is close to that, is there. So we'll go for minus 26.3 joule per kg Kelvin, which is close to this. So we'll go for option A. Okay. So, and yeah, I guess we have answers key at the end. So you can check all the answers. Whatever we got, we can see the numbers 83.33, 6.6, minus 116, 287, and minus 198, and all these numbers we can remember. Anyhow, I'll be sharing you this PPT, no issues. So is that clear to all of you? Did we do something big and complicated today? No, correct? So to answer gate questions, basics are the only things that are required to us. Okay. And if you see whatever we have done purely based on basics. In the 11th question, tomorrow I'll start availability and irreversibility, basically exergy. Okay. And in maths, I'll teach you numerical methods, no issues. You can definitely after completion of probability and statistics, I'll teach you numerical methods. Vamsi, have something to talk with 11th question. Let me check. What is this 11th question? 11th question. Yeah, this is the 11th question. Okay. In 11th question, it is given adiabatic. If we apply adiabatic condition between volume and temperature, then we will get same temperature. No, we don't get, because the process is irreversible. And ideal gas, I mean, this PV power gamma equal to constant, TV power gamma minus 1 equal to constant is only applicable for reversible adiabatic process. Okay. And because we have taken the assumptions that the process is reversible. But if you see here, some irreversibility is taking place because of the friction that is getting generated. So, we can't say that the same temperature you will get when you apply this TV power gamma minus 1 equal to constant. Okay. Clear? Vamsi, did I clear you? Are you all understanding the concepts? Please tell me, genuinely, are you all understanding the things? I'll share you in Telegram channel. Chinao, no issues. Okay. So if you're understanding the things, then that's the happiest part. Okay. Then we'll wind up this session. I think we have made a bit long session today. It's 11:44. It's 11:44 already. So if you have something to write, you can write in the comment box, not in the live chat, in the comment box of the video. Okay. So you can always add there. Fine. Thank you all. Then have a nice day.